Good evening, class. I am Mohit, and today I will be solving assignment number 12. So there will be 10 questions, which are based on the NPTEL lectures of Electronic Theory of Solids course 2025. Okay. So there will be 10 questions which I will be solving. These kind of problems have been discussed in the class and motivated by the class lectures only. Solving these problems will give you more insights on the concepts which you have learned in the class. It will be kind of the revision, and will also the numericals problem which I'll be solving, which will give you better insight on how to approach these kinds of problems and solve when given parameters are there, and to extract a unknown parameter based on the whatever the valid assumptions of the BCS theories. So having said that, so I will start with the very first question, which says that in quantum computing, what is superposition? So that is the question. That in the quantum computing, it's a very famous renowned word nowadays because of quantum computing, these qubits kind of thing, which are supposed to break the barriers of the classical computer computation power, because they will be having multiple bits. In that sense, they can do more of the computation in a very given short span of time. So that's the idea with the quantum computing. So addressing this question, so let's see one by one the options. The ability of a classical bits to store multiple values simultaneously. No, this is not right, because classical bits can only store classical bits can only store values which are 0 or 1. It cannot take in between values. Only one of these are allowed in the classical mechanics. The second, so the first option is this is false. Now coming to the second option, the representation of classical information using quantum bits. No, this is also false. Why it is false? It's not a classical information. Information is quantum. That is, they it's it is described in terms of wave function, in terms of superposition of wave function, unlike classical mechanics of wave function. So the second one is also false. Now coming to the third one, the phenomenon where qubits can exist in multiple states at the same time. This is true. So in quantum mechanics, superposition is a fundamental principle. It's a fundamental principle where a qubit in a combination of the basis states zero and one simultaneously. Unlike classical bits that can take 0 or 1 at any time only. So a quantum qubit is one which is superposition of both the states, and that will allow the quantum computers to process a massive number of possible at once. So the phenomena where qubits can exist in multiple states at the same time is true. Now the fourth is the process of converting classical algorithm into quantum algorithm. No, this is not about algorithm. It is more about how information is stored. That is in terms of wave function. In terms of wave functions. So option number 4 is also false. So the true statement for this case is that in a quantum computing, superposition is the phenomena where qubits can exist in multiple states at the same time. And with what kind of operator you probe, what is the operator, according to that, the state collapses and gives you the information at given time. Now, moving on to the second problem, which is what is Andre reflection in the context of the superconductivity. So, Andre reflection is the reflection which occurs, like for example, if you have a normal metal, let me draw that normal metal, and you have a superconductor. So this is superconductor which has Cooper pairs, and this is normal metal. Yeah. So in this case, if there is an there will be a reflection across the boundary between normal metal and the superconductor. So when an electron from the normal metal, for example, this electron, this approaches the superconductor and has energy below the superconducting gap, it cannot enter as a single particle. Instead, what will happen? It will pair up with another electron and forming a Cooper pair. So it will form a Cooper pair that will go inside, and a hole will be directed back, will be reflected back. Reflected hole. That's what it is. And this process is known as Andre reflection. So Andre reflection, Andrew reflection occurs at the boundary between a normal metal and a superconductor. When electron from the normal metal approaches towards this superconductor, since its energy is less than the superconducting gap, it cannot go through the superconductor. So what will happen? It will form a Cooper pair with the electron, and a hole will be reflected back because the net charge has to be constant, right? So if there is one electron here, electron is going home, so minus of E, that is the hole, will be generated here in this case, and this is known as the Andre reflection. Now let's look at the given options. The first option is the process of reflecting electrons off the surface of the superconductor. Just not the process of reflecting of the of electrons. It's not the electrons, it's the hole which is getting reflected. So this is false. Reflection of a quasi-particle at the interface between normal metal and the superconductor. This is true because this hole which is called, it's a quasi-particle. So this is true. Third option is the reflection of a photon by superconducting material. No, there is no need of photon here. A type of quantum entanglement observed in superconducting circuit. No, false. It's not regarding any quantum entanglement. Quantum entanglement means there are two particles which are entangled. So if you measure the one, you can tell the states of the other particle. So that's quantum entanglement. So the correct option for this question, that what is the Andrew reflection in the context of superconductivity? It is the reflection of a quasi-particle at the interface between a normal metal and a superconductor. Okay. If this is clear, then I will move on to the problem number 3, which is which of the following is true regarding the relation between the phase of the BCS wave function phi and the number of occupied pairs n. So if you observe it, then you will find that this is an uncertainty relation between the number of Cooper pair. This is an uncertainty relation between the number of Cooper pairs and global phase phi. Phase of BCS function is the global phase phi of the BCS wave function. That's in the superconductor, we all know. So it's conceptually similar to the position momentum uncertainty relation in quantum mechanics. So the number phase uncertainty relation states that the uncertainty in the number of the particles and the uncertainty in the phase satisfies the relation delta n delta phi has to be greater than equal to 1. And this reflects a trade-off, kind of. A well-defined phase implies a large uncertainty in the number of the particles, as in superconductor, and conversely, a fixed number of particles means the phase is uncertain, which is more like an insulating state. So that's the correct answer. So in this case, delta n delta phi has to be larger than 1. So this is the correct option. If this thing is clear, then let's move on to the next problem, which is what is the primary function of a squid in the field of superconductivity? So before coming to these options, let's understand what is a squid. As you can get the information from the name only, squid is superconducting quantum integrated device. What does it means? So how squid is made? So squid is like you take a cone kind of thing, which is like an insulator kind of thing, which is made up of the superconducting material, and here both are connected by an insulator. This is an okay, this is an insulator. So this is an insulator, and these are like superconducting ring. So if you see it from the top, it will be more like one superconductor here, superconductor, and they are separated by this insulator. And you give the signal here, you give the signal here, kind of thing. If you see it from the top view, insulator, and this is superconductor. So it's like a coil, right? With the insulator in between. So If there is a magnetic field, the flux which is passing through in this one and the charge which takes this path and this path, they will be having a different phase. And when they pass through this insulator kind of thing, and then they interfere, and their interference gives the information about the magnetic field. Yeah. So that's the idea behind the squid, and it can measure a very small magnetic field up like 10 power minus 15 Tesla order magnetic field can be measured with the squid. So even a very small magnetic field it can sense. So let's look at the options now. So generating magnetic field for medical imaging, no, false. It do not generate the magnetic field. That magnetic field. It senses the magnetic. It's a sensor. Detecting and measuring extremely weak magnetic field. True. Stabilizing superconducting circuits, false. It don't have any role in stabilizing the superconducting circuits. Amplifying quantum signals in quantum computer, no, false. Quantum signals and quantum computer, it's not an amplifier. That's what it is. So it's a sensor which can detect extremely weak magnetic fields. If this is clear, then I'll come on to the question number 5, which is in a squid, what is the critical principle exploited to measure extremely small magnetic field? Quantum tunneling, Josephson effect, Meissner effect, or Landau penetration depth. So, what is quantum tunneling? Quantum tunneling is like you have a barrier whose height is more than the energy of your states wave function basically. So classically, this region is forbidden. Forbidden. This region is forbidden. So particle cannot be found here. So if there is a wave, it should not go. But what we found, and the quantum mechanics says that the wave function will decay exponential, and there will be a finite probability of finding the particle here also. And this is not a quantum tunneling. The principle on which the STM, scaling tunneling microscope work, all those things. But this does not have to do anything with the squid, because in the squid, but you have these two superconductors which are separated by a very thin layer of insulator. So the insulator, this superconductor. Right? And in that case, the Cooper pair tunnels through this insulator. So that's known as Josephson effect. So this is false. Josephson effect is true in squid. Meissner effect is like in fact in which if you have a superconductor, diamagnetism, right? It repel the applied external magnetic field. So that is Meissner effect. But it does not have to do anything with this Squid-Josephson junction effect. So this is also false. And London penetration depth is the depth through up to which the magnetic field penetrates. So this is also false. So the correct answer here is Josephson effect for the squids. If that is clear, then I will move on to the next question, which is consider a Josephson junction with a critical current IC of 2 microamp, voltage of 1 microvolt. Calculate the Josephson junction energy EJ using the relation EJ is equals to H bar by 2 E ICV, where H bar is given, everything is given. You'll have to just calculate the EJ. So EJ is the energy for the Josephson junction basically. So it's the energy which is required to pass that basically that insulator region. So EJ is H bar by 2E IV, right? So EJ is equals to H bar is 1.054 into 10 power minus 34. I is 2 microamp 10 power minus 6. V is 1 into 10 power minus 6. 2 into 1.6 into 10 power minus 19. And if you do the computation of it, I think what one will get is this will be EJ 1.054 into 10 power minus 34 divided by
divided by 3, 2 goes, and it will be 1.6 into 10 power minus 19, and if you combine the power it will be 10 power minus 12. So EJ will be 3.29 into 10 power minus 24 joule. So yeah, that's the energy for the EJ for this question. Okay. If that's clear, then let's move on to the problem number 7, which is in an experiment, a niobium wire of radius 0.25 mm is immersed in liquid helium. Temperature T is equals to 4.2 Kelvin. I is 300 amps. What is the magnetic field inside the current carrying the wire? Correct answer up to 2 decimal. We know the current carrying wire magnetic field, right? So B is equals to mu naught I by 2 pi R. That's the magnetic field, which is by current carrying wire. So B is equals to mu naught is 4 pi into 10 power minus 7. I is 300. 2 is 2. Pi is 3.1. Pi is pi. And R is radii is 0.25 into 10 power minus 4. 10 power minus 3. So it will be 0.24 Tesla. So that's the answer for this problem. 0.24 Tesla. If that's clear, then I will move on to the next problem. If you have any question or doubt, you can ask in the comment section. I'll be addressing the question. So question number 8 is, in the context of a Josephson effect, what happens when a direct current flows through a Josephson junction? So yeah, taking this question, yeah, when a direct current less than critical current flows, when a direct current less than critical current flows through a Josephson junction, a supercurrent passes through the insulating barrier without any voltage across the junction. This means no energy is dissipated. The current flows by the tunneling of the Cooper pairs. I is equals to IC sine phi, where IC is the critical current, phi is the phase difference between the superconducting wave function on either side of the junction. So let's look at the options now. The Josephson junction becomes resistive dissipative energy as heat. False. If DC current is less than IC, then it won't happen. So quantum vortices form within the junction disruptive superconductivity. This is also false. This only happens if the I is greater than IC. The Josephson current is modulated by an external magnetic field. This is also false. Josephson junction current does not get modified by the external magnetic field. A non-zero supercurrent flows through without any voltage drop across the junction. Yes, this is true. If the phase difference is there, then the non-zero supercurrent will always flow through the Josephson junction without any voltage drop. Now the question number 9 is to determine the temperature at which the critical field becomes half of its value at 0 Kelvin. If the critical temperature is Tc, we know the relation H is equals to Hc Tc square. So what the question is saying is the temperature at the critical field becomes half of its value at 0 Kelvin. So H is Hc by 2 is equals to Hc 1 minus T square by Tc square. If that's the case, Hc goes 1 by 1 minus 1 by 2 T square by Tc square is equals to 1 by 2. T is equals to Tc by root 2. So option A is correct. T is equals to Tc by root 2. Now moving on to the problem number 10. In the context of a topological insulator, what distinguishes their behavior from conventional insulator? So topological insulators are the insulators which is like behave the insulator in the bulk but have conducting surface states. So if you have a graphene sheet and you put it in the magnetic field like quantum Hall effect, its edge will be conducting. There will be edge mode like this. There will be edge mode, bulk insulator, edge conducting, topological insulator. And how many edges will be there on the conductivity is governed by Chern number. Chern number is nothing but the phase which the electron acquires when it goes in that K space in the band structure. So that's the Chern number, and the Chern number will be non-zero for topological insulator. So let's address the questions one. So it happens when the system breaks the time reversal symmetry, then the topological insulator things comes up, and they are very robust towards the impurity and all those things. So their phase don't get destroyed easily with the impurities or these kind of things. So they are very robust, and they are that's why they are proposed to be the futuristic kind of the phases in which the quantization will be very sharp, the resistance will be very sharp, 25812 for h by e square. So the question answer number one is topological insulator always exhibit metallic behavior. False. They are insulator in the bulk. Topological insulators have conducting surface despite being insulating in the bulk. This is true. Topological insulator can only exist at extremely low temperature. This is false. It's not like that. At high temperature also, they people have seen it like WTE2 all those ones. Topological insulator do not follow Ohm's law. They follow. So this is also false. The correct option here is B, true, which is topological insulator have conducting surface state despite being insulating in the bulk. So this is the correct answer for the question number 10. Now I will wait for, in the last class, a guy asked about the Vogel wave kind particle. So I'll just go over it once. So Vogel quasi particle. So it is a concept. So superconductivity theory. That describes the collective excitation of superconductor, particularly in the context of BCS theory. So, in a superconductor, the electron form a Cooper pair, we all know, with pairs of electrons with opposite momentum and a spin that moves without resistance. So, these Cooper pairs are in the superfluid state, and the traditional notion of individual electron does not fully describe the behavior of the system. So, the Boligo quasi-particle, Boligo quasi-particle emerge as a way to describe excitations. The states which is above the ground state of the superconductors, disturbance or deviation above the ground state of superconductor. SC means superconductor, where Cooper pairs can break apart. But the pair can be assigned into different energy states. So in the Bogoliubov case, one hole and one electron gets when you give enough energy to a Cooper pair, they break apart, and then the quasi-particle which gets generated is an electron in a hole kind of thing, and that's the Bogoliubov quasi-particle concept. So with this one, we'll get 10 minutes for Q&A session, and if there's no question answer, then we'll close the class, and this is the last class for this course. So all the best for your exams.